All right, listen up. Welcome to this EASA M7.6 Fits and Clearances B1 Test Prep Explainer. Out here on the hangar floor, there's absolutely no room for guesswork. We are dealing with precise metal, heavy loads, and literally people's lives. Let's dive right into the exact fits, clearances, and tolerances you need to know to pass your test, and more importantly, to do the job right.
Section 1. Tolerances and wear limits. Let's get straight to it. Look, these textbook numbers, they are absolutely not suggestions. They are our physical reality. Plain tolerance is simply the difference between the minimum and maximum of a given dimension. Simple enough. Next, we have dimensional tolerance. Now, this is the allowable variation specifically designed to achieve proper function. Basically, this ensures the part can actually handle real-world conditions like thermal expansion and heavy operational load without jamming. And finally, bilateral tolerance is the variation of the design size in both directions, plus and minus. You respect these limits, or things fall apart mid-flight. Okay, let me challenge you for a second. See, you're holding a part that's been working hard for 1,000 flight hours. How do you know when it crosses the line from just being, nicely worn in to being absolute garbage? What exactly is a permissible worn dimension, and where do you look to find those hard, unyielding limits? Here's the deal. The permissible worn dimension is strictly the size to which a part may wear before it must be rejected as unserviceable. It is your absolute cutoff line before you toss that piece straight into the scrap bin. And where do you find these wear limits? Strictly in the appropriate repair overhaul manual. Those limits are based on rigorous engineering stress tests. That manual is your Bible on the floor. You never guess, you always look it up. Moving on to Section 2, the basis of fits. Let's look at how these parts actually mate together on the bird. You're going to hear a lot about the hull basis and the shaft basis. The distinction is pretty straightforward. The hull basis is a system of fits relating to the basic or nominal size of the hull. The shaft basis, on the other hand, is a system of fits relating specifically to the nominal shaft size. Out here, we mostly use the hull basis in manufacturing. Why? Because it is just so much easier and cheaper to machine a standard hull and then slightly vary the shaft to fit into it. So knowing that, visualize you're working at the bench. You've got clearance fits, where parts just slide together easily, and interference fits, where you really need some serious force to mate them. But what happens mechanically when you're working with a transition fit? Well, a transition fit is that tricky middle ground. The loosest case gives you a clearance fit, but the tightest case gives you an interference fit. Mechanically speaking, we use these when exact dead-on alignment is absolutely critical, but we might still need to take it apart someday. So depending on the exact machining tolerances, you might just slip it in by hand, or you might need to tap it in with a mallet. All right, Section 3, precision drilling and reaming. Let's put the manuals down for a second. Grab your tools. This is where your hands need to be as precise as your eyes. I'm going to test your actual procedure here. If you need a perfectly sized glass-smooth hole that requires a reamer, how do you size the initial drill bit you plunge into the metal before you ream it? Here's the golden rule of the shop. If a hole is to be reamed, it must be drilled slightly smaller than its nominal size. You always drill slightly undersized. Why? Because the reamer isn't a drill, it's a finishing tool. It needs actual material to shave off the walls to get that perfect, precise finish and final dimension. If you just drill it to nominal size right off the bat, the reamer has absolutely nothing to bite into and you've ruined the tolerance entirely. Next up, Section 4, shaft twist and bowing. Keep your safety glasses on and come over to the inspection bench with me. We need to look at some heavy structural deformation. Take a look at these damaged shafts. Now, don't just tell me they're broken. I need you to distinguish the damage. Mechanically speaking, what is the exact difference between a shaft that is bowed and one that is twisted? This brilliantly illustrates the basic physics of aircraft loads. If the center line of the shaft is no longer straight, the item is bowed. Basically, it's been bent off-center. On the other hand, twist is the direct result of applied torsion on the shaft. Bowing comes from a lateral load or a hard impact, while twisting comes from excessive rotational force. Two completely different forces causing two completely different types of damage. Now, think about the metal's elasticity. Say you see a shaft under massive rotational load, and it's physically twisting. But the very moment you remove that heavy force, the twist in the shaft entirely disappears. It just snaps back to normal. What does that tell us about the load that was applied? Well, it tells us we got incredibly lucky. If the twist disappears entirely, then the shaft was loaded below its elastic limit. The metal's molecular structure essentially acted like a giant spring and just bounced back without suffering any permanent plastic deformation. But listen to me, we never just rely on luck or eyeball it to see if a shaft is permanently deformed. When you need to measure the exact amount of twist in a shaft to see if it is still within legal limits, you use a strain gauge. Lock that into your memory right now. Torsion equals twist, and twist is measured with a strain gauge. Almost done. Section 5. Wear and concentricity checks. All right, apprentice, we are entering the final phase of the shift. Time to separate the amateurs from the pros. We've got a heavy jack screw assembly sitting right here. These things take an unbelievable beating adjusting the stabilizer. So what specific precision measuring tools do you need to go check out from the tool crib right now to examine this jack screw for wear? You literally cannot eyeball a jack screw. They are examined for wear strictly with a micrometer or a vernier caliper. The reasoning is pretty simple. The thread profiles wear completely unevenly under constant aerodynamic friction. You have to measure down to the thousandth of an inch to ensure those threads won't just shear off under flight loads. Okay, here is your final test before I let you loose on the actual floor. We need to check if a high-speed shaft is running perfectly true or if it's wobbling. What is the exact step-by-step physical procedure for testing the concentricity of a shaft on the bench? Do not skip a step here, okay? Concentricity is tested by first placing the shaft in V blocks, or between centers. This isolates the shaft and provides a true datum reference. Second, you rotate the shaft slowly entirely by hand. Third, you read the measurements under a dial test indicator. That indicator is hypersensitive. It'll show you exactly how much runout or wobble you have as that shaft completes a full 360-degree rotation. We covered a ton of ground today, everything from basic dimensional tolerances to measuring twist with a strain gauge, all the way to checking concentricity with a dial test indicator. Remember, these aren't just answers you bubble in on an EASA B1 test. These are the cold, hard engineering realities that keep an aircraft from falling out of the sky. Grab your micrometer. Are you ready to trust your measurements when a flight depends on it? Because out here on the hangar floor, that is exactly what you have to do every single shift. Study these facts, know your manuals inside and out, and I'll see you on the next explainer.